Good evening, and welcome back to Plane Crash for Sleep. I'm glad you're here. Wherever you are in the world tonight, get comfortable, dim the lights, and let's begin our journey together through one of aviation's most complex and tragic stories. Tonight we're traveling back to November 12th, 2001, to a clear, crisp morning in New York City. The sun was rising over the Atlantic Ocean, painting the sky in shades of orange and pink, casting long shadows across the runways of John F. Kennedy International Airport. It was the kind of morning that makes pilots smile. Clear visibility, light winds, perfect flying weather. Just 2 months after the world watched towers fall and the city's skyline change forever, just 2 months after that terrible Tuesday in September, another aircraft would fall from the sky over Queens. But this time, the enemy wasn't terrorism. It wasn't a deliberate act of violence. It was something far more subtle, far more insidious. A perfect alignment of training assumptions, design characteristics, and human reactions that would tear an aircraft apart at 2,000 feet, revealing uncomfortable truths about the gaps between what pilots believed, what they were taught, and what was actually true about the magnificent machines they flew. This is the story of American Airlines Flight 587, a morning departure to the Dominican Republic that would become the second deadliest aviation accident in United States history, surpassed only by the 1979 crash of American Airlines Flight 191 in Chicago. 265 people, 251 passengers, 9 crew members, and 5 residents on the ground below would lose their lives in a catastrophe that would shake New York's Dominican community to its very core and reveal uncomfortable truths about how we train pilots, how we design aircraft, and how easily good intentions can lead to tragic consequences when critical information isn't fully understood or properly communicated. The vertical stabilizer, that towering tail fin that keeps an aircraft pointed true through the sky, would snap off in mid-flight and fall into Jamaica Bay. Not from a bomb hidden in the cargo hold, not from metal fatigue after years of service, not from a maintenance error or manufacturing defect, but from the very control inputs meant to save the aircraft, from a pilot doing exactly what he had been trained to do, responding to a routine situation in a way that seemed correct based on everything he had learned, but was actually catastrophically wrong. It's a story that begins not with malice or negligence, but with the dangerous gaps between perception and reality, between simulator and sky, between what seems right and what actually is. It's a story about how even the most sophisticated systems, operated by the most skilled professionals, can fail when underlying assumptions prove false. And it's a story about how a community, 2 communities really, came together in grief and have worked for more than 2 decades to ensure that those who died are never forgotten, and that the lessons learned from their deaths continue to save lives in the skies above us every single day. The year 2001 was a watershed in aviation history, though not for reasons anyone would have chosen. The September attacks had changed everything overnight. Security protocols that had been in place for decades were suddenly inadequate. Armed guards patrolled airports. Passengers arrived hours earlier for domestic flights. Cockpit doors that had once been opened mid-flight to let children visit were now reinforced and locked. The traveling public was nervous, scared, looking at their fellow passengers with suspicion. Airlines were hemorrhaging money as business travel collapsed and leisure travelers stayed home. Insurance premiums skyrocketed. The entire industry was reeling, trying to figure out how to maintain operations in a world that suddenly felt much more dangerous. And yet, on the morning of November 12, 2001, Flight 587 was fully booked, as it nearly always was. Every single one of its 251 seats was filled. This wasn't just any route, you see. This wasn't just another flight on the schedule. For New York's Dominican community, which numbered over 600,000 people in 2001 and has only grown since, this flight was more than transportation. It was more than a way to get from point A to point B. It was a cultural institution, a bridge between two worlds, a vital connection between the lives people had built in New York and the homeland many still called home. It was the early flight, the one that departed around 8 in the morning and got you to Santo Domingo by early afternoon, in time for lunch with family, in time to start a vacation, or handle urgent business, or attend a wedding or a funeral. It appeared in Dominican songs and movies. There was a famous song by Johnny Ventura, literally titled Flight 587. Characters in Dominican films would talk about taking Flight 587. In Washington Heights, the vibrant Dominican neighborhood in Upper Manhattan, people would say, "See you on the 587," the way others might say, "See you on the train." In 2001, aviation was still absorbing lessons from the previous decade, still evolving, still learning. The industry had come a long way since the early days of commercial flight. Jets had replaced propeller aircraft. Navigation systems that once relied on radio beacons and dead reckoning now used satellite guidance. Weather radar could see storms from miles away. Ground proximity warning systems could alert pilots before controlled flight into terrain. Collision avoidance systems could detect other aircraft and provide escape guidance. The cockpit had evolved from a collection of analog gauges to computer displays, showing vast amounts of information at a glance. And new materials, composite materials made of carbon fiber reinforced plastics, were becoming more common in commercial aircraft, promising lighter weight, better fuel economy, and potentially lower maintenance costs. The Airbus A300-600 that would fly as Flight 587 that morning had a vertical stabilizer made entirely of this advanced composite material, attached to the fuselage through composite lugs rather than traditional aluminum fittings. It was state-of-the-art engineering when the aircraft was designed in the early 1980s. The composite tail was lighter than an aluminum one would have been, and according to Airbus, it required less maintenance. Visual inspections and simple tap tests with a coin could detect damage, or so the theory went. The aircraft had been in service since July 1988, when it was delivered new to American Airlines. It had been flying for over 13 years, accumulating thousands of flight hours, carrying millions of passengers safely across the Americas and beyond. But the aviation industry in 2001 was also grappling with something more subtle, something less visible than new materials or computer systems. It was grappling with the challenge of training pilots for a new generation of aircraft, with different handling characteristics, different response curves, different assumptions about how pilots would interact with the controls. The industry was transitioning from purely mechanical flight controls, cables and pulleys and hydraulic actuators directly controlled by pilot inputs, to more sophisticated systems, with computers mediating between pilot and aircraft, systems that could provide protections and enhancements that made flying easier and safer, but that also created new challenges in understanding exactly how the aircraft would respond to control inputs. Different manufacturers approached this transition differently. Boeing tended toward systems where the pilot felt more directly connected to the aircraft, where moving the control column produced a relatively direct aerodynamic response. Airbus tended toward more mediated systems, where computers interpreted pilot intentions and executed them in ways designed to keep the aircraft within safe operating parameters. Neither approach was inherently better or worse. They were simply different philosophies, each with advantages and disadvantages, each requiring pilots to understand the specific characteristics of the aircraft they were flying. And American Airlines, like many carriers around the world, was working to develop training programs that would prepare pilots for upset conditions and unexpected situations in these new aircraft. Their Advanced Aircraft Maneuvering Program, or AAMP, was designed with the best of intentions. It was meant to teach pilots how to recover from dangerous situations, unusual attitudes, stalls, wake turbulence encounters, situations that pilots might encounter rarely or never in a normal career, but that required immediate and correct responses when they did occur. The program used sophisticated flight simulators to create realistic scenarios, or at least scenarios that seemed realistic. The program would prove to be tragically flawed in ways that wouldn't become apparent until it was far too late, until the lessons had been learned in the worst possible way. The aircraft itself, registration number N14053, was truly a marvel of modern engineering. An Airbus A300B4-605R, one of the first of the R model A300-600s ever built, where the R stood for Extended Range. Its first flight had been in December 1987, rolling down the runway at Airbus's facility in Toulouse, France, lifting off into European skies for the first time. By November 2001, it had been flying for American Airlines for over 13 years, a veteran of the fleet, carrying millions of passengers safely across the Americas. The aircraft was powered by two General Electric CF6-80C2A5 engines, each a masterpiece of engineering in its own right, each capable of producing over 52,000 pounds of thrust, enough to push this massive machine, weighing over 300,000 pounds fully loaded, through the air at speeds approaching 600 miles per hour. The A300 was a wide-body twin-engine jet, one of the first truly successful wide-body twins, proving that you didn't need 3 or 4 engines to safely cross oceans or carry large numbers of passengers. The cabin was spacious, comfortable by the standards of economy-class air travel. The aircraft could carry 251 passengers in American Airlines 2-class configuration, 16 in business class up front, 235 in economy. And on this morning, every single one of those seats was filled. There wasn't an empty seat on the plane. Families traveling together, business travelers, vacationers, people going home, people visiting relatives, each with their own story, their own reasons for being on this flight, their own lives and dreams, and people waiting for them at the other end. This particular aircraft had a history, though nothing that raised particular concern at the time or suggested any special risk. In 1994, 7 years before the accident, it had encountered severe turbulence that injured dozens of passengers. The incident was thoroughly investigated. The aircraft was inspected. No structural damage was found. It was returned to service. During its original construction at the Airbus factory in Toulouse, there had been some delamination, separation of layers, in part of the vertical stabilizer. This was caught during quality control inspections, repaired according to established procedures, inspected again, and certified as airworthy before delivery. None of these incidents seemed significant at the time. They were just part of the aircraft's operational history. Aircraft encounter turbulence. Manufacturing processes sometimes have minor issues that are caught and corrected. The aircraft had passed all its inspections, completed all its maintenance checks on schedule, and was considered fully airworthy in every respect, according to all applicable regulations and standards. The crew that morning represented years of professional aviation experience and thousands of hours in the sky. Captain Edward States, 42 years old, married with children, had been with American Airlines since July 1985, over 16 years with the company. He had come up through the ranks the traditional way, starting as a flight engineer on older aircraft, progressing to first officer, then to captain. He held an airline transport pilot certificate, the highest level of pilot certification, and an FAA first-class medical certificate with no restrictions. According to American Airlines records, He had accumulated over 8,000 hours of total flight time, with more than 3,400 hours as pilot in command and over 1,700 hours as pilot in command specifically on the A300. He knew this aircraft intimately. He had flown it in all weather conditions, in and out of airports all across the Americas. His last recurrent training, the regular training that all airline pilots undergo annually to maintain proficiency, had occurred from June 18th to 22nd, 2001, just 5 months before the accident. His last recurrent proficiency check, where his flying skills were evaluated by a Czech airman, was on June 21st, 2001. His last pilot-in-command line check, where he was evaluated while flying actual revenue flights, occurred on July 31st, 2001. All of these checks had been passed satisfactorily. FAA records indicated no accident or incident history and no enforcement actions against his certificate. He had flown approximately 146 hours in the 90 days before the accident and 52 hours in the 30 days before the accident, well within normal operating parameters, enough to maintain proficiency without being so much as to cause fatigue. He had flown a trip that started on the morning of November 9th and ended on the night of November 10th. He had November 11th off, a day to rest at home with his family. According to his wife, he went to bed at a reasonable hour on the evening of November 11th, planning to wake early for the morning departure. He knew First Officer Sten Moline well. They had flown together on 36 flight segments before this one. His wife stated that he and Moline got along well, that he enjoyed working with Moline, that there was good crew coordination between them. First Officer Sten Moline, 34 years old, was at the controls as the pilot flying that morning. On airline flights, one pilot is designated as the pilot flying, actually manipulating the controls, while the other is the pilot monitoring, handling radio communications, monitoring instruments, and providing backup. The roles alternate between flights, with captains and first officers taking turns. On this morning, it was Moline's turn to fly, which meant his hands were on the control column and his feet were on the rudder pedals when the wake turbulence hit. Moline had been with American Airlines since March 1991, over 10 years with the company. Before American, he had flown for commuter and regional airlines, operating smaller aircraft under less demanding conditions, building experience and hours the way most professional pilots do. His father, Stan Moline, was a retired Eastern Airlines captain who had flown for over 30 years, who had operated just about every aircraft in Eastern's fleet, the Lockheed Electra, the Boeing 727, the massive Lockheed L-1011 widebody. The elder Moline had taught his son to fly, had encouraged his career, though he never pushed. When Sten announced during his freshman year at the University of Rhode Island that he wanted to become a professional pilot, his father was thrilled. Sten had done his pilot training at Bolivar Flight Academy in Tennessee, then worked his way up through the regional airline system, getting laid off several times during the inevitable downturns and consolidations that plagued that part of the industry, but always finding another position, always accumulating more hours, more experience, more type ratings. Moline held an airline transport pilot certificate and an FAA first-class medical certificate dated October 18, 2001, less than a month before the accident. With one limitation, he was required to wear correcting lenses while exercising the privileges of the certificate, a common restriction for pilots who need glasses. He had received his type rating on the A300 in November 1998, 3 years before the accident. According to American Airlines records, he had over 4,400 flight hours total, with over 1,800 hours specifically on the A300. He had flown approximately 137 hours in the 90 days before the accident, and 51 hours in the 30 days before the accident. His last recurrent training had occurred from December 21, 2000 to January 5, 2001, almost exactly 11 months before the accident. His last recurrent proficiency check was on December 23, 2000. By all accounts from the pilots who flew with him, Sten Moline was an excellent pilot. One captain who flew with him multiple times, Captain Louis Mers, rated him as an 8.5 out of 10. Another captain, John Lavelle, stated that Moline's flying skills were excellent and that he had hands of silk, aviator speak for smooth, precise control inputs. He was described as professional, competent, pleasant to work with. But there was something else in his history, something that would prove tragically significant, though no one realized it at the time. Captain Lavelle had noted in an interview conducted months after the accident that Moline had one unusual tendency. He could be very aggressive on the rudder pedals when encountering turbulence. On one occasion, in a Boeing 727, during a climb-out with flaps still partially extended, what pilots call flying dirty, the aircraft had encountered wake turbulence. Moline had responded by making rapid rudder inputs, 1, 2, 3, very fast, alternating left and right. Lavelle thought they had lost an engine. He asked Moline what he was doing. Moline said he was leveling the wings due to wake turbulence. Lavelle noted that the wings weren't moving, but he could feel the yawing moments, the side-to-side forces throughout the aircraft. He experienced side load, side load, side load. On another occasion, in an A300, when they encountered the wake of a Boeing 737, Moline had immediately made the decision to execute a go-around, adding full power and climbing away. There was no discussion, no hesitation. He saw wake turbulence, he reacted aggressively. He believed he was doing the right thing. He had been trained to respond to turbulence, and he did. He believed that rapid control inputs were the appropriate response to wake turbulence encounters, that this was how you saved the aircraft, that this was proper procedure. And why wouldn't he believe that? In American Airlines' Advanced Aircraft Maneuvering Program, in the sophisticated flight simulators at the airline's training facility, he had practiced these scenarios. The simulator would create a wake turbulence encounter from a Boeing 747, causing the simulated aircraft to roll dramatically, sometimes as much as 90 degrees of bank, wing pointing straight at the ground, a terrifying upset condition. The correct response, he was taught, was to use rudder to counter the roll, to get the wings level quickly. And in the simulator, it worked. He would make aggressive rudder inputs, the simulated aircraft would stabilize, the turbulence would pass, and the instructor would nod approvingly. Exercise completed successfully. He had done what he was supposed to do. He had saved the aircraft. Or so it seemed. The 7 flight attendants that morning were experienced professionals, each with years of service with American Airlines, each trained to handle emergencies, each dedicated to passenger safety and service. Deborah Fontakis, Barbara Gianasca, Wilmer Gonzalez, Joseph Lopez, Michelle Mills, Carol Palm, William Valdespino. 7 individuals with their own lives, their own families, their own dreams and plans. They reported for duty that morning, went through their pre-flight briefings, checked emergency equipment, reviewed procedures, then boarded the aircraft and began preparing the cabin for passengers. They had no reason to think this would be anything other than another routine flight. Another morning departure to Santo Domingo. Another day at work. The passenger cabin was filled with 251 people, and their demographics tell a story about this flight and its significance. Approximately 90% of the passengers were of Dominican descent. Some lived in New York and were traveling to visit family. Some lived in the Dominican Republic and were returning home after visiting New York. Some were vacationers. Some were traveling for business. There were children traveling with parents. There were elderly passengers traveling alone. There were young professionals. There were entire extended families traveling together. This flight was known throughout Washington Heights, that vibrant Dominican neighborhood in Upper Manhattan, where the streets are filled with Spanish conversations, where bachata and merengue pour from shops and restaurants, where community is strong and family ties extend across thousands of miles of ocean. In Washington Heights and other Dominican neighborhoods across New York, there was a saying: "Every Dominican in New York has either taken Flight 587 or knows someone who has." It got you there early. It got you there in time for what you needed to do. And there was a culture around it, an etiquette, almost a style. People would dress up for Flight 587. It was part of the experience. A quote from Belkis Lora, a relative of a passenger, captured it perfectly. "Every Dominican in New York has either taken that flight or knows someone who has. It gets you there early. At home, there are songs about it." The flight had achieved a kind of cult status, not just transportation, but a cultural phenomenon, woven into the fabric of the Dominican diaspora experience in New York. On the morning of November 12, 2001, passengers began arriving at John F. Kennedy International Airport's Terminal 4, Gate 22, well before the scheduled 8 o'clock departure. JFK is one of the busiest airports in the United States, serving over 60 million passengers a year, a hub for international travel, its terminals sprawling across more than 5,000 acres in Queens. On a normal day, it's a bustling, energetic place. But this was not a normal day. This was 2 months after September 11th. Security was dramatically tighter than it had ever been. Armed National Guard troops patrolled the terminals. Every bag was scrutinized. Every passenger was questioned. Random searches were common. The atmosphere was tense, nervous. People arrived even earlier than usual, knowing that security screening would take longer. The whole process had become slower, more intrusive, necessary perhaps, but also anxiety-inducing. Families said their goodbyes in the terminal. Children clutched stuffed animals. Business travelers checked their laptops one more time, made last-minute phone calls. People chatted in Spanish, in English, mixing languages the way bilingual communities do. There was excitement, people going on vacation, going home, going to see family they hadn't seen in months or years. There was also the underlying nervousness that all air travel carried in those months after September 11th. Every passenger looked at their fellow travelers differently now. Every unattended bag triggered concerns. Every unexpected sound caused heads to turn. But people still flew, because they had to. Because life goes on, because the alternative, letting fear stop you from living, was unacceptable. The aircraft pushed back from the gate around 9 o'clock, about an hour behind schedule due to the enhanced security procedures and the time required to board 260 people in the post-9/11 security environment. Captain States sat in the left seat, the traditional position for the captain. First Officer Moline sat in the right seat. Between them, the center pedestal held the throttles, the flap controls, the various switches and displays that manage the aircraft systems. Above them, the overhead panel contained even more switches and circuit breakers and indicators. In front of them, the instrument panel showed the electronic flight displays, artificial horizons, navigation displays, engine instruments, all the information they needed to fly the aircraft safely. They ran through their checklists with the practiced efficiency of professionals who had done this hundreds of times before. Before engine start checklist, engine start procedures. After engine start checklist, taxi checklist. Each item called out, checked, confirmed. The pre-flight inspection had revealed no issues. All systems were operating normally. The weather was clear, visibility excellent, winds light, temperature cool but not cold. It was absolutely perfect flying weather, the kind of morning when flying is pure pleasure, when the sky is welcoming and everything feels right with the world. They received their taxi clearance from ground control and began moving away from the gate, the tug disconnecting, the aircraft rolling under its own power now. They followed the yellow taxiway lines that crisscross every major airport, threading through the complex geography of runways and taxiways and ramps. Other aircraft were moving too. FedEx freighters heading to cargo gates, passenger jets from dozens of airlines taxiing to and from gates. The constant choreographed dance that happens at a major airport every minute of every day. They taxied to runway 31 left, the left one of two parallel runways, oriented roughly northwest-southeast. The 3-1 means the runway heading is approximately 310 degrees magnetic, and the L designates it as the left runway of the pair. It was a long taxi, several minutes of slow rolling, following ground control instructions, stopping at hold short lines, waiting for crossing traffic, then continuing. Ahead of them, also waiting for departure, was Japan Airlines Flight 47, a Boeing 747-400 jumbo jet bound for Tokyo. The 747 is one of the largest passenger aircraft in the world, instantly recognizable with its distinctive hump, a massive machine with a wingspan of over 200 feet and capable of carrying over 400 passengers. This particular 747 was at maximum takeoff weight, or close to it, preparing for the long trans-Pacific flight. When something that large moves through the air, especially during the high-power climb-out after takeoff, it leaves behind a wake, invisible but very real vortices of spinning air that trail from the wingtips. These vortices are areas of intense rotational airflow, spiraling currents that can persist for several minutes, especially in calm conditions with little wind to dissipate them. They tend to sink and drift laterally behind the aircraft, following the contours of the wind. For a small aircraft following a large one, wake turbulence can be severe, even dangerous, causing rapid rolling motions that can be difficult to control. For a large aircraft like an A300 following a 747, the effect is usually much less severe. Uncomfortable, perhaps, requiring pilot attention, but not inherently dangerous if handled properly. Air traffic control was well aware of this phenomenon. Wake turbulence is a known hazard in aviation, covered extensively in pilot training, and controllers are trained to maintain adequate separation between aircraft, particularly when a smaller aircraft is following a larger one. The standard procedure is to maintain a minimum separation, usually at least 2 minutes for an aircraft of the A300 size following a heavy jet like the 747, or 4 nautical miles of horizontal distance if following the same departure route. At 9:11 minutes 08 seconds, Japan Airlines Flight 47 was cleared for takeoff. Japan Air 47, runway 31 left, cleared for takeoff, came the controller's voice. The massive 747 began its takeoff roll, its 4 engines producing nearly 200,000 pounds of combined thrust, accelerating the million-pound aircraft down the runway, faster and faster, until finally the nose lifted and the massive jet rotated into the air, climbing away into the morning sky, leaving behind it those invisible, swirling vortices. At 9:11 minutes 36 seconds, the tower controller issued a routine caution to Flight 587, still waiting at the hold short line. American 587 Heavy, runway 31 left, traffic's a Japan Air 747 just airborne. Caution wake turbulence, runway 31 left, line up and wait. This was standard procedure, the wake turbulence caution given whenever an aircraft follows a heavy jet, a reminder to be prepared for possible turbulence. American 587 Heavy, came the acknowledgement from Captain States. His voice was calm, professional, routine. They knew about wake turbulence. Every pilot does. It's covered extensively in ground school, in flight training, in recurrent training. It's a basic element of aviation knowledge. The question that each pilot and each airline answers somewhat differently is, what's the appropriate response when you encounter it? At 9:13:28, nearly 2 minutes and 20 seconds after the Japan Airlines departure, American Airlines Flight 587 received its takeoff clearance. American 587 Heavy, runway 31 left, cleared for takeoff. First Officer Moline, as the pilot flying, Acknowledge the clearance and advance the throttles. The two General Electric engines spooled up to full takeoff power, their turbines spinning at thousands of revolutions per minute, compressing air and igniting jet fuel, producing that characteristic roar that you can feel in your chest. The aircraft began to accelerate down the runway, pushing the crew and passengers back in their seats with that familiar sensation of acceleration, the G-forces building as speed increased. The runway rolled beneath them, faster and faster. 60 knots, 80 knots, 100 knots. V1, the decision speed, the point beyond which you're committed to flying even if an engine fails. Then VR, rotation speed. Moline pulled back gently on the control column. At 9:14:29, the nose wheel lifted off the pavement, the aircraft's attitude changing from nose down to nose up. A moment later, at about 135 knots, the main landing gear left the ground. Flight 587 was airborne, beginning its climb into that clear blue November sky. The aircraft climbed smoothly through 500 feet, establishing a positive rate of climb, the landing gear retracting into the wheel wells with the characteristic thump that passengers feel, the flaps beginning to retract as airspeed increased. At 9:15:00, Captain States made initial contact with the departure controller, switching from tower frequency to departure frequency. American 587 Heavy out of 1300 for 5,000. They were at 1,300 feet, climbing to their initial assigned altitude of 5,000 feet. The departure controller responded immediately, his voice clear and professional. American 587 Heavy, New York departure, radar contact, climb and maintain 13,000. They were now cleared to climb to 13,000 feet, the first step in their journey to cruise altitude. Everything was proceeding normally. The aircraft was performing as expected. The engines were producing full power. The systems were all functioning correctly. The city of New York spread out below them, Manhattan to the left with its distinctive skyline, forever changed by the absence of the Twin Towers. Queens directly ahead, with its grid of streets and neighborhoods. Brooklyn and the Atlantic Ocean beyond. Long Island stretching to the east. It was a beautiful view on this crystal-clear morning. The aircraft entered a climbing left turn, banking gently to about 15 to 20 degrees of bank, a standard turn to intercept the assigned departure route, following the flight path that would take them out over the Atlantic before turning south toward the Caribbean. The turn was smooth, coordinated, exactly as it should be. Passengers were settling in, fastening seatbelts being secured, flight attendants beginning to move through the cabin, checking that everyone was properly seated and secured. Some passengers were already pulling out books or magazines. Others were looking out the windows at the receding cityscape below. The flight data recorder would later show with cold precision exactly what happened next, second by second, tenth of a second by tenth of a second, providing investigators with an exact timeline that could be correlated with the cockpit voice recorder, with air traffic control recordings, with witness statements, allowing them to reconstruct the sequence of events with certainty. At 9:15:36, at an altitude of approximately 1,600 feet, still in the climbing left turn, Flight 587 encountered the wake turbulence from Japan Airlines Flight 47. The separation between the two aircraft at this point was well within safe limits, at least 4.3 nautical miles horizontally and about 3,800 feet vertically. The 747 was well ahead and significantly above them, climbing rapidly on its own departure path. But the wake vortices from that massive aircraft, those invisible spiraling currents of air, had drifted and sunk, and now Flight 587 flew into them. The aircraft jolted suddenly, a sharp, violent movement that rattled the cockpit and cabin, a sensation like driving over a large pothole at high speed. Coffee cups shifted, Passengers grabbed armrests. In the cockpit, the control column moved in Moline's hands, the aircraft responding to the turbulent air, rolling slightly to the right. This was not unusual or unexpected. Wake turbulence feels uncomfortable, but for an aircraft the size of the A300, it's typically not dangerous. It's annoying, certainly. It gets passengers' attention, but aircraft are designed to handle it, and pilots encounter it regularly, especially at busy airports where aircraft follow each other in relatively quick succession. The standard response, the response taught to every airline pilot, is to maintain control of the aircraft but let the turbulence pass without overreacting. Ride it out. The vortices are localized. You're in them for just a few seconds, and then you're through them and into smooth air again. But First Officer Moline's response was not to ride it out. His response, trained into him through American Airlines' Advanced Aircraft Maneuvering Program and reinforced through practice in the simulator, was to take active control measures. He had been taught that wake turbulence required an aggressive response. He believed that using the rudder to counter the aircraft's motions was the correct procedure, and so he did exactly what he had been trained to do. At 9:15:44, 8 seconds after the initial wake turbulence encounter, as the aircraft continued to experience turbulence and rolling motions, Moline applied full left rudder input. Let me pause here to explain what the rudder does and how it works, because this is central to understanding what happened next. The rudder is the movable vertical surface at the rear of the vertical stabilizer, that tall fin at the tail of the aircraft. When the rudder deflects to the left, it creates an aerodynamic force that pushes the tail of the aircraft to the right, which makes the nose of the aircraft yaw to the left. When it deflects to the right, the opposite happens. Tail goes left, nose goes right. The rudder is primarily used for directional control, especially during crosswind landings or in the event of an engine failure. In normal flight, the rudder is used for coordination, keeping the aircraft flying straight relative to its direction of travel, preventing side slip. On the A300, the rudder system was designed to be highly responsive. It required relatively light pedal forces to produce large rudder deflections. This was a design choice that made the aircraft easy to handle in normal flight, gave good control authority, allowed precise control inputs. But it also meant that full rudder inputs, mashing the pedal all the way to its stop, could occur quickly and easily, without the pilot feeling the kind of heavy pedal forces that might have provided a tactile warning that something extreme was happening. The system was power-assisted, hydraulically actuated, meaning the pilot's foot pressure wasn't directly moving the rudder against aerodynamic forces. Instead, the pilot was commanding the hydraulic system to move the rudder, and the hydraulic system did the heavy lifting. When Moline applied full left rudder at 9:15:44, the rudder deflected to its maximum left position. This created an aerodynamic force on the vertical stabilizer. The aircraft's nose began to yaw left. But the turbulence continued. The aircraft's rolling motions continued. And within seconds, the aircraft's motion had changed. Now it seemed to be rolling the other way. At 9:15:50, just 6 seconds after his first input, Moline reversed the rudder. Full right rudder. The rudder swung from full left deflection to full right deflection. The aerodynamic forces reversed. Now the tail was being pushed left, the nose yawing right. And then, as the aircraft responded to that input, as the nose swung to the right and the rolling motion changed again, Moline reversed the rudder once more. At 9:15:52, full left rudder again. Back and forth, left to right to left, full deflection inputs in rapid succession, each one commanding the rudder to move to its maximum travel in one direction then immediately commanding it to move to its maximum travel in the opposite direction. What Moline didn't know, what he couldn't know, because he had never been taught, because American Airlines' training program had never explained it, because the simulator behavior had reinforced incorrect beliefs, was that each of these inputs was doing something catastrophic to the aircraft's structure. Every time the rudder moved, it created aerodynamic loads on the vertical stabilizer. At flight speed, even at the relatively modest speed of about 250 knots that they were flying, the forces are enormous. When you change the angle of a surface moving through air, you change the pressure distribution across that surface. And with a surface as large as the A300's rudder and vertical stabilizer, the forces involved are measured in tens of thousands of pounds. But it wasn't just the magnitude of the forces that mattered. It was the pattern. It was the fact that the forces were alternating, pushing one way, then immediately pushing the opposite way, then pushing the first way again, over and over in rapid succession. Think of bending a paper clip. If you bend it once, it bends. If you bend it back, it bends back. But if you keep bending it back and forth, repeatedly, eventually the metal fatigues and fails. Not because any single bend exceeded the metal's ultimate strength, but because the alternating stresses, the cyclic loading, weakened the material until it could no longer hold together. Now imagine that paperclip is a 28-foot-tall structure made of composite materials, layers of carbon fiber fabric embedded in resin, each layer oriented in a specific direction to provide strength and stiffness. And instead of your fingers bending it, aerodynamic forces equivalent to hundreds of thousands of pounds are pushing it back and forth. Each push stresses the material. Each reversal stresses it in the opposite direction. The loads build, add up, accumulate, exceed any single load case that the designers anticipated or tested for. At 9:15:54, Moline made another rudder reversal, his fifth input. Full right rudder. The rudder swung from maximum left to maximum right deflection. The flight data recorder later showed that the aerodynamic loads on the vertical stabilizer had already reached nearly twice the certified limit load. The structure was being stressed in ways it was never designed to handle, ways that the certification process had never considered, ways that seemed impossible, because why would a pilot ever make these kinds of inputs? The vertical stabilizer is one of the most critical structures on an aircraft. It provides directional stability. It's what keeps the aircraft pointed straight ahead, what prevents the nose from wandering left and right, what maintains coordinated flight. On the A300-600, this structure was made entirely of composite materials. Not because composite was necessarily better for this application, but because it was lighter, and lighter meant better fuel economy and more payload capacity. The vertical stabilizer weighed approximately 2,800 pounds, significantly less than an equivalent aluminum structure would have weighed. The structure consisted of a large fin with the rudder attached to its trailing edge. The fin itself was built up from hundreds of layers of carbon fiber fabric, each layer carefully laid in place and oriented to provide strength in specific directions. Some layers ran span-wise, from root to tip. Some ran chord-wise, from leading edge to trailing edge. Some ran at angles. The combination of all these layers, when cured together with epoxy resin, created a structure that was stiff and strong, that could handle significant loads while weighing less than metal. The fin was attached to the aircraft's fuselage through 6 lugs, 3 on the left side and 3 on the right side, projecting from the base of the fin and fitting into metal fittings embedded in the fuselage structure, held in place by large metal pins. These lugs were also made of composite material, built up from many layers of carbon fiber, designed and tested to handle the loads that the vertical stabilizer would transmit to the fuselage. The lugs were positioned front, center, and rear on each side, distributing the loads across 6 attachment points. This was all state-of-the-art engineering, carefully designed and thoroughly tested. Airbus had conducted extensive testing of the vertical stabilizer, both on test stands and in flight. They had loaded the structure to its limit loads, the maximum loads expected during the aircraft's operational life. They had loaded it to 1.5 times the limit loads, the ultimate loads, the loads the structure must withstand without failure, providing a safety margin. The vertical stabilizer had passed all these tests. It met all certification requirements. It was approved by aviation authorities in Europe and the United States. But every structure has limits, and those limits are defined by the design envelope, range of loads and conditions that the designers anticipated and tested for. Aircraft certification standards require that structures withstand certain loads based on certain assumptions about how the aircraft will be operated. For the vertical stabilizer, the design envelope included loads from side slip when the aircraft flies at an angle to its direction of travel. It included loads from rudder deflections, but specifically single rudder deflections, not rapid alternating deflections. It included loads from gusts and turbulence. It included combinations of these loads. What the design envelope didn't include, what the certification standards at the time didn't require consideration of, was rapid alternating full rudder inputs. Why would they? It wasn't a normal flight condition. It wasn't something pilots were supposed to do. It wasn't a scenario that made sense. Who would repeatedly slam the rudder from full left to full right to full left? It would be like repeatedly stomping on the gas pedal and brake pedal of a car at the same time. It wasn't a use case that needed to be designed for. Except that First Officer Molen was doing exactly that. And he was doing it because he had been trained to do it. He was doing it because, in the simulator, it had worked. He was doing it because he believed it was the correct response to wake turbulence. He was doing what every professional aviator tries to do. He was trying to save the aircraft, trying to protect his passengers and crew, trying to fulfill his responsibilities as pilot in command of the situation. At 9:15:58, just 22 seconds after the initial wake turbulence encounter, just 14 seconds after Molen's first rudder input, the right rear lug failed. The composite material, subjected to loads far beyond anything it was designed to withstand, loads alternating in direction faster than the material could respond, loads building and building with each rudder reversal, simply failed. The lug fractured. And once one lug failed, the loads that it had been carrying were instantly redistributed to the remaining lugs. Those lugs, already stressed to their limits, couldn't handle the additional load. Within fractions of a second, the failure propagated. One lug after another failed in quick succession. The entire vertical stabilizer separated from the aircraft, tearing away from the fuselage, tumbling backward and down into Jamaica Bay, more than a mile north of where the aircraft would eventually crash. Inside the cockpit, there was a loud bang, the unmistakable sound of catastrophic structural failure, the sound of the tail tearing away from the fuselage, a sound so distinctive and so terrifying that pilots who have heard the cockpit voice recorder playback describe it as haunting. Then came another sound, even more terrifying, the roar of air rushing against the aircraft. Without the vertical stabilizer streamlining the aft fuselage, air was battering against surfaces that were never designed to be exposed to such airflow. Warning alarms began sounding, multiple alarms overlapping, the aircraft's systems detecting conditions that should not exist, trying to warn the crew, trying to give them information that might help them save the situation if it could be saved. But it couldn't be saved. Without the vertical stabilizer, the aircraft had no directional stability. Nothing was keeping the nose pointed forward. Nothing was preventing yaw. The aircraft's nose immediately pitched down sharply, diving toward the earth. The aircraft began to yaw violently, the nose swinging left and right, back and forth, the fuselage essentially weather vaning in the airflow, spinning around the center of gravity. At 9:16:01, just 3 seconds after the vertical stabilizer separated, the engines, subjected to massive aerodynamic loads that they were never designed to handle, loads that twisted and flexed the wing, loads that exceeded the structural capability of the engine mounts, tore away from the wings. The right engine separated first, shearing away from its mount points on the right wing, plummeting earthward like a missile, ultimately crashing into a residential area several blocks north of where the aircraft's main wreckage would impact. The left engine followed almost immediately, separating from the left wing and falling toward the neighborhood below. Each engine weighed nearly 9,000 pounds and was falling from over 2,000 feet. When they hit the ground, they would hit with devastating impact force. The loss of the engines meant the loss of electrical power from the engine-driven generators. The flight data recorder, which ran on electrical power from the engines, stopped recording at 9:16:01. The cockpit voice recorder, running on emergency battery power from the aircraft's emergency bus system, would continue recording for 13 more seconds, capturing the final moments in the cockpit, recording the sounds and voices of two pilots facing the absolute worst-case scenario, an uncontrollable aircraft, certain death rushing toward them. At 9:16:04, 3 seconds after the engine separated, the stall warning sounded, a loud, continuous horn indicating that the aircraft was on the edge of aerodynamic stall, about to lose the ability to generate lift, about to simply fall out of the sky. But the stall warning was almost irrelevant at this point. There was no recovery possible. Without a vertical stabilizer, without engines, with the aircraft in an uncontrolled descent, tumbling and spinning, there was nothing the pilots could do. Every pilot's training, every instinct, every procedure in every manual assumes that you have control. When you don't, when the aircraft simply won't respond to control inputs, when the very structure you need to control the aircraft is gone, there's nothing to do but hold on and wait for the impact. At 9:16:07, First Officer Moline's voice came over the cockpit voice recorder, strained but remarkably controlled given the circumstances. "What the hell are we into?" A pause, perhaps a second. "We're stuck in it." His voice showed the stress, the realization that something terrible was happening, but also the professionalism, the continued attempt to communicate, to understand, to somehow find a solution even when none existed. And then Captain states, his last words, captured forever on that cockpit voice recorder, "Get out of it! Get out of it!" You can hear the urgency, the command, the desperate hope that maybe, somehow, Moline can still save this, can still find a way to recover control, can still pull them out of this impossible situation. But there was no way out. The aircraft was doomed. The laws of physics and aerodynamics are inflexible, unforgiving. An aircraft cannot fly without directional stability. An aircraft cannot be controlled without control surfaces. An aircraft that is tumbling and spinning and diving toward the Earth at over 200 miles per hour cannot be saved. At 9:16 14 seconds Edens, the cockpit voice recorder stopped. The aircraft had slammed into the ground at the intersection of Newport Avenue and Beach 131st Street in Bell Harbor, a quiet residential neighborhood on the Rockaway Peninsula in Queens. A community of single-family homes and small apartment buildings, a place where people raised families and went to work and lived ordinary lives far removed from the glamour and chaos of Manhattan, just a few miles to the west. The aircraft hit with devastating, apocalyptic force. At the speed it was traveling, probably close to 300 miles per hour at impact, the kinetic energy was immense. The aircraft essentially disintegrated on impact, breaking apart into thousands of pieces, the fuselage fragmenting, the wings shearing off and cartwheeling down the street, components scattering across multiple blocks. Fire erupted instantly, inevitably. Jet fuel igniting on impact, tens of thousands of pounds of fuel creating an inferno, flames shooting hundreds of feet into the air, black smoke billowing up into that clear blue sky. The heat was intense enough to ignite houses, to set trees and cars on fire, to create secondary fires that spread through the neighborhood. 3 houses were destroyed immediately on impact, literally obliterated, reduced to smoking rubble and shattered foundations. Several other houses were damaged, some severely, some less so. Windows shattered for blocks around from the shock wave and the heat. Debris rained down across a wide area. Pieces of aircraft, pieces of houses, unidentifiable fragments of what had moments before been an aircraft carrying 260 people and all their possessions, all their hopes and plans. All 251 passengers died instantly. The forces at impact were so extreme that death was instantaneous, literally faster than nerve signals could travel, faster than the brain could process what was happening. All 9 crew members died, the 2 pilots in the cockpit and the 7 flight attendants in the cabin, all of them killed instantly by the unsurvivable impact forces. And on the ground, 5 more lives were lost. 5 people who were simply in their homes on an ordinary Monday morning, having breakfast or getting ready for work, or perhaps still sleeping in after a weekend. People who had no connection to aviation, no involvement in any of the factors that led to this crash, but whose lives were nonetheless ended by an aircraft falling from the sky. Helen Concannon and her husband Thomas Concannon were in their home when the aircraft hit. They died together. Kathleen Lawler and her son Christopher Lawler were also killed. Franco Pomponio, another resident, also died. 5 people, 5 families, suddenly and without warning, experiencing the worst phone call or knock on the door anyone can imagine. Your loved one is gone. An aircraft crashed. They didn't suffer, but they're gone, and they're never coming back. Belle Harbor is a close-knit community, a neighborhood where everyone knows everyone, where neighbors look out for each other, where community ties are strong. The area is predominantly Irish-American, families who have lived here for generations, firefighters and police officers and teachers and small business owners, people who work hard and raise families and take pride in their community. This community had already been devastated by September 11th. Belle Harbor and the broader Rockaway community had the highest concentration of firefighters in New York City. When the towers fell, firefighters from Rockaway rushed to Manhattan, and many of them never came home. Dozens of Belle Harbor residents had died at the World Trade Center just 2 months earlier. The neighborhood was still in mourning, still processing those losses, still attending funerals and memorial services, still trying to understand how the world had changed so dramatically and so suddenly. And now this. Now an aircraft crashing into their homes, killing more neighbors, bringing fire and destruction to streets where children had been playing just hours before, where families had been having breakfast, where life was supposed to be safe and normal. The trauma was indescribable. Residents ran from their homes, not knowing if the aircraft was going to hit their house next, not knowing if there were more aircraft falling from the sky, not knowing if this was another terrorist attack. Children were crying. Adults were screaming. The emergency calls flooded 911. Within minutes, fire trucks and ambulances and police cars were racing toward Belle Harbor from all across Queens and Brooklyn, sirens wailing, not knowing what they would find, but knowing it was bad. The timing of the crash, just 2 months after September 11th, immediately raised fears of terrorism. This was everyone's worst fear come true. Another aircraft, another attack, another mass casualty. The event. The Empire State Building was immediately evacuated. United Nations headquarters went into lockdown and then was evacuated. Major buildings across New York implemented emergency procedures. Subways slowed or stopped. Bridges and tunnels were monitored intensively. Federal agents rushed to the scene. Air Force fighters were scrambled over New York City. The question on everyone's mind, the question being asked on news broadcasts and in the halls of government and in homes across America, was this another attack? For hours, uncertainty reigned. Eyewitnesses reported seeing the tail separate from the aircraft. Some witnesses reported seeing the engines fall away. Some reported seeing fire. Some reported hearing explosions. The reports were confused, contradictory, incomplete, as eyewitness reports always are in chaotic situations. But the pattern didn't immediately suggest terrorism. Terrorists don't typically target aircraft leaving New York for the Dominican Republic. The timing, mid-morning on a Monday, not a Friday or Sunday when more people fly, didn't fit terrorism patterns. And physical evidence at the crash site didn't show signs of explosion or fire before impact. FBI agents and NTSB investigators worked side by side at the crash site, carefully documenting everything, collecting evidence, interviewing witnesses. The vertical stabilizer was found in Jamaica Bay, about a mile north of the main wreckage site, floating in the water, recovered by Marine units within hours of the crash. The engines were found blocks away from the impact site, embedded in residential properties, having crashed through roofs and walls before coming to rest. The wreckage pattern was consistent with an in-flight breakup, the vertical stabilizer separating first, then the engines, then the fuselage descending and impacting terrain. It was not consistent with an explosion or missile strike or deliberate crash. Investigators found no evidence of explosive residue on the recovered wreckage, no evidence of blast damage, no evidence of missile impact, no evidence of fire before impact, no evidence of tampering with the aircraft, no evidence of anything other than structural failure. By the evening of November 12th, less than 12 hours after the crash, investigators could say with reasonable confidence, this was not terrorism. This was structural failure. But why? Why would a vertical stabilizer separate from an aircraft in mid-flight? This was unprecedented in modern commercial aviation. Tails don't just fall off of aircraft. What could have caused this? The investigation would be led by the National Transportation Safety Board, the independent federal agency responsible for investigating civil aviation accidents in the United States. The NTSB is one of the most respected safety investigation organizations in the world, known for thorough, methodical, evidence-based investigations that identify not just what happened, but why it happened and what can be done to prevent it from happening again. They are not interested in assigning blame or liability. That's for courts and lawyers. They're interested in truth and safety. The NTSB assembled a team of investigators representing expertise in structures, systems, operations, human factors, materials, survival factors, and more. Representatives from the Federal Aviation Administration, American Airlines, Airbus, General Electric, the Allied Pilots Association, the Association of Professional Flight Attendants, and numerous other parties joined the investigation. Hundreds of people would ultimately contribute to the investigation, which would take nearly 3 years to complete, and would produce one of the most comprehensive accident reports in NTSB history. The first task was to recover and document the evidence. The main wreckage was spread across multiple blocks in Bell Harbor. Every piece, every fragment had to be photographed, documented, and collected. The vertical stabilizer and attached rudder were pulled from Jamaica Bay by Marine salvage units and transported to a hangar at JFK Airport for initial examination. The engines were carefully extracted from the houses they had crashed into and transported to secure facilities. The flight data recorder and cockpit voice recorder were recovered from the wreckage and sent to the NTSB laboratory in Washington, D.C. for readout and analysis. The vertical stabilizer became the focus of intense scrutiny because this was unprecedented. This was the first time in modern commercial aviation that a composite vertical stabilizer had separated from a large commercial aircraft in flight. The structure was transported to NASA's Langley Research Center in Virginia, one of the premier aerospace research facilities in the world, home to expertise in composite materials that dated back decades. NASA Langley had the equipment and the knowledge necessary to examine this structure in unprecedented detail, to understand how it failed and why.
Investigators carefully documented every fracture surface, every failed attachment point, every detail of the failure. They cut small sections called coupons from undamaged areas of the stabilizer to test the material properties, to verify that the composite had been manufactured correctly, to ensure that the material met specifications. They examined the 6 composite lugs that had attached the stabilizer to the fuselage, studying in microscopic detail how and why each one had failed. They used computed tomography scans, essentially medical CAT scans, to look inside the composite structure without cutting it apart, to search for pre-existing damage or delamination, or voids that might have weakened the structure. They went layer by layer through sections of the composite structure, physically separating the layers under microscopes, counting the layers, checking their stacking sequence, verifying their orientation against the engineering drawings. They performed mechanical tests on material samples, loading them to failure, measuring their strength and stiffness, comparing the results to design values. They ran sophisticated computer simulations of the loads on the structure, modeling the aircraft's flight path, the control inputs, the aerodynamic forces, calculating exactly how much load was placed on each part of the vertical stabilizer at each moment in time. The analysis took months. Teams of engineers and scientists worked long hours, examining evidence, running tests, analyzing data, trying to piece together exactly what happened and why. And gradually, painstakingly, a clear picture emerged. The composite material was manufactured correctly. It met all specifications. The layup was correct, the right number of layers and the right orientations. There was no pre-existing damage that contributed to the failure. The structure had performed exactly as designed, exactly as it should have. It had simply been subjected to loads far beyond what it was designed to withstand, loads that no commercial aircraft vertical stabilizer should ever experience in normal operations, or even in reasonably foreseeable abnormal operations. The flight data recorder provided the crucial evidence that allowed investigators to understand exactly what happened. This device, often called a black box, though it's actually bright orange, records hundreds of parameters from the aircraft systems: airspeed, altitude, heading, attitude, engine parameters, control surface positions, accelerations, and dozens of other measurements, all sampled multiple times per second. The recorder for Flight 587 had recorded everything up until the moment the engine separated and power was lost. Investigators could see every control input, every aircraft response, every change in flight parameters. They could reconstruct the flight second by second, creating animations and graphs that showed exactly what the aircraft did and exactly what loads were placed on its structure. The data showed the wake turbulence encounter at 9:15:36. The aircraft experienced a rolling disturbance, nothing extreme, bank angle changing by perhaps 10 to 15 degrees, well within the aircraft's normal operating envelope. The data showed Molin's first rudder input at 9:15:44, 8 seconds after the wake turbulence encounter. Full left rudder. the rudder deflected to its maximum position. The data showed the aircraft's response: yaw to the left, side force on the fuselage, increasing loads on the vertical stabilizer. The data showed each subsequent rudder reversal, the alternating inputs, the building loads. The data showed that by the time of the final rudder input, the aerodynamic loads on the vertical stabilizer had reached approximately 203,000 pounds of force in one direction, more than twice the certified limit load of 100,000 pounds, and significantly beyond the certified ultimate load of 150,000 pounds. The structure had been stressed well beyond its design capability, beyond what any reasonable design process would have anticipated, beyond what certification standards required it to withstand. But the question remained: why? Why did an experienced, well-trained professional pilot make these inputs? This became the focus of intense investigation. Investigators interviewed dozens of American Airlines pilots, asking about training, about procedures, about how pilots were taught to respond to wake turbulence. They examined training records, simulator scenarios, and training materials. They interviewed instructors and check airmen, and gradually, a picture emerged of a training program that, despite good intentions, had inadvertently taught pilots to respond in ways that could be dangerous under certain circumstances. American Airlines' Advanced Aircraft Maneuvering Program had been designed to prepare pilots for unusual situations, for upsets and unusual attitudes and emergency conditions. The program used sophisticated flight simulators to create realistic scenarios. But the word realistic is important here, because not all aspects of the simulator were realistic in ways that mattered. In one scenario commonly practiced, the simulator would create a wake turbulence encounter from a Boeing 747. The simulated turbulence would cause the aircraft to roll dramatically, sometimes as much as 90 degrees of bank angle, wing pointing straight at the ground, a terrifying and extreme upset. The correct response taught in this scenario was to use rudder to counter the roll, to level the wings quickly using rudder inputs. And in the simulator, it worked. Pilots would make aggressive rudder inputs. The simulated aircraft would respond. The wings would level, the turbulence would pass, and the scenario would end successfully. Exercise completed. Pilots came away with the clear lesson that wake turbulence could cause extreme upset, and that aggressive rudder use was the appropriate response. But there were problems with this. Scenario. First, the severity was unrealistic. Real wake turbulence from a 747, while uncomfortable, typically causes bank angle changes of only 5 to 10 degrees for an aircraft the size of the A300, not 90 degrees. The scenario was exaggerated for training purposes, to give pilots practice with large upset recovery. But this exaggeration wasn't clearly explained to pilots. They weren't told, "This scenario shows a 90-degree bank that you would never actually experience from wake turbulence. We're exaggerating it for training purposes." They were left with the impression that wake turbulence could actually cause these extreme conditions. Second, and more critically, the simulator's behavior during these scenarios didn't accurately represent what would happen in the actual aircraft. During certain upset recovery scenarios, the simulator's flight control system behaved differently than the actual aircraft system, particularly with regard to rudder effectiveness. When pilots made aggressive alternating rudder inputs in the simulator during upset scenarios, those inputs didn't create the extreme loads they would create in the actual aircraft. The simulator's flight model didn't accurately capture the structural loads created by rapid rudder reversals. The turbulence would subside, the aircraft would stabilize, and pilots would attribute the recovery to their rudder inputs, not realizing that in the real aircraft, those same inputs would have created dangerously high structural loads. This was a subtle but critical disconnect between simulation and reality.
The simulator reinforced behavior, aggressive rudder use for wake turbulence, that was actually dangerous in the real aircraft. Pilots practiced this behavior repeatedly. It became ingrained, automatic, a trained response. When Moline encountered wake turbulence on Flight 587, he did what he had been trained to do, what he had practiced dozens of times in the simulator, what he believed was correct procedure. He didn't know that his actions were destroying the aircraft's structure. He had no reason to know. Nothing in his training had taught him that rapid rudder reversals were dangerous. Nothing in the simulator had shown him the consequences. Beyond the training scenarios, there was also a widespread misunderstanding among pilots about something called maneuvering speed, denoted by the symbol VA. This is an important concept in aircraft operations. Maneuvering speed is defined as the speed below which full deflection of any single control surface cannot overstress the aircraft structure. Below VA, if you move the yoke all the way to the stop or push the rudder pedal all the way to the floor, the aircraft will stall before structural limits are exceeded. It's a built-in protection. But, and this is critical, this protection applies only to single control inputs in a single axis. It applies to one full aileron input, then returning to neutral and stabilize flight, or one full elevator input, then returning to neutral. It applies to each control axis independently. It does not apply to multiple rapid control inputs. It does not apply to alternating inputs. It does not apply to simultaneous inputs in multiple axes. Aircraft are designed with the assumption that pilots will make single control inputs, assess the situation, and return to stabilized flight before making another input. This is a reasonable assumption for normal flight operations, but many pilots, including those at American Airlines, misunderstood the protection that VA provides. They believed that flying below VA provided complete protection from structural damage, no matter what control inputs were made. They believed that they could make any combination of control inputs, in any pattern, at any rate, and as long as they were below VA, the aircraft structure was protected. This misconception was widespread in the industry. It wasn't corrected in training. It wasn't addressed in manuals. It was simply a gap in understanding that persisted because it had never been tested, never been challenged by events. Flight 587 was flying at approximately 250 knots when the wake turbulence encounter occurred. The maneuvering speed for the A300 at that weight and configuration was about 270 knots. They were below VA. Based on the widespread misunderstanding of what VA means, Moline might have believed that his rudder inputs, being made below maneuvering speed, couldn't possibly damage the aircraft structure. He would have been wrong, but he wouldn't have known he was wrong until it was too late. The NTSB also examined the design of the A300's rudder system itself. As mentioned earlier, the system was designed to be responsive, requiring relatively light pedal forces to produce significant rudder deflections. The system was hydraulically powered, meaning the pilot's foot pressure didn't directly move the rudder against aerodynamic forces. Instead, the pilot commanded the hydraulic system, and hydraulics did the actual work of moving the rudder. This made the system easy to use, provided precise control, allowed fine adjustments. But it also meant that a pilot could make very large, very rapid control inputs without receiving strong tactile feedback about what they were doing. In an aircraft with manual flight controls, cables and pulleys directly connected to control surfaces, making a full rudder input at high speed would require significant force, and the pilot would feel the resistance, would feel that they were doing something extreme. In the A300's power-assisted system, full rudder inputs required only moderate pedal force. It was easy to make large inputs, perhaps too easy. The NTSB's final report, adopted and released in October 2004, nearly 3 years after the accident, determined that the probable cause was the in-flight separation of the vertical stabilizer as a result of the loads beyond ultimate design that were created by the first officer's unnecessary and excessive rudder pedal inputs. But the report very carefully and deliberately identified contributing factors, making clear that this was not simply pilot error, that the accident resulted from a complex interaction of factors. The contributing factors identified included characteristics of the A300-600 rudder system design and elements of the American Airlines Advanced Aircraft Maneuvering Program. The report made clear that the training program had encouraged pilots to use rudder in ways that could create dangerous structural loads, that the simulator scenarios had reinforced this training in ways that didn't accurately represent the real aircraft, and that pilots had widespread misunderstandings about structural protection at speeds below VA. The report noted that the first officer had a demonstrated tendency to use aggressive rudder inputs, but placed this in context. He used aggressive inputs because he had been trained to do so. The report generated some controversy. Some felt it placed too much blame on the first officer. Others felt it didn't place enough blame on Airbus for the rudder system design, or on American Airlines for the training program. Families of victims struggled with the findings. How could good training be bad training? How could doing what you were taught be wrong? How could an experienced pilot's attempts to control the aircraft lead to its destruction? The answers were complex, unsatisfying, frustrating, but they were also true. This was a systemic failure, a failure that occurred at multiple levels, a tragedy that resulted not from one person's error, but from accumulated gaps in understanding, communication, and oversight. The accident led to sweeping changes. American Airlines immediately revised its Advanced Aircraft Maneuvering Program. The training now emphasized that rudder should not be used for roll control during upset recovery. It taught pilots about the dangers of rapid alternating control inputs. It made clear that VA protection applied only to single control inputs. The FAA issued airworthiness directives requiring inspections of vertical stabilizers on A300 and A310 aircraft. Airlines around the world reviewed their training programs. Simulator vendors reviewed their flight models. Eventually, in 2009, American Airlines retired its entire fleet of A300 aircraft from service, replacing them with newer, more efficient aircraft. But the changes went further and lasted longer. The NTSB issued 15 recommendations to the FAA and to French aviation authorities. These recommendations covered training, certification standards, structural design requirements, and more. Some were implemented quickly. Others took years. In 2022, more than 20 years after the accident, the FAA issued a final rule requiring new design standards for all transport category aircraft. Aircraft with powered rudder control surfaces must now be designed to withstand loads caused by rapid reversals of the rudder pedals. This was a fundamental change to aircraft certification requirements, directly traceable to Flight 587. Meant to ensure that future aircraft could withstand the kinds of control inputs that destroyed Flight 587, even if pilots never should make those inputs. The legacy of Flight 587 extends far beyond regulatory changes. The accident fundamentally changed how the aviation industry thinks about the interaction between pilot training, simulator fidelity, and aircraft design. It revealed that training programs can inadvertently teach incorrect responses if not carefully validated against real aircraft behavior. It showed that simulators, if not carefully calibrated, can reinforce dangerous behaviors. It demonstrated that pilots need to understand not just how to operate an aircraft, but also the limitations of the aircraft's structure and the consequences of control inputs. It showed that assumptions built into certification standards, such as the assumption that pilots would only make single control inputs, needed to be re-examined. For the families of those who died, the investigation's findings were complex and difficult to accept. There was no simple villain to blame, no terrorist to capture and punish, no obvious mechanical failure that could be fixed, no clear negligence that could be sued. Instead, there was a complicated story of well-intentioned people making decisions based on incomplete information, of systems that seemed robust but had hidden flaws, of training that seemed thorough but taught lessons that were incomplete or incorrect. Some families found comfort in the changes that resulted from the accident, in the knowledge that their loved ones' deaths led to improvements that would save other lives. Others found the explanations unsatisfying, feeling that someone must be at fault, that the pilot or the airline or the manufacturer must bear responsibility. First Officer Moline's father, Stan Moline, struggled deeply with the investigation's conclusions. He listened to the cockpit voice recorder tape and heard something different than what the investigators described. Where they heard Moline making control inputs, Stan heard his son asking for help, trying to communicate a problem. He believed that there might have been pre-existing problems with the rudder system or electrical systems that contributed to the accident. He worried that the investigation had focused too narrowly on pilot actions and not broadly enough on potential aircraft malfunctions. He spoke to witnesses who saw the crash, trying to gather information that might support a different explanation. His grief was compounded by the sense that his son was being blamed for a tragedy that had far more complex causes, that the pilot was being made the scapegoat, while systemic failures in training and design were downplayed. The debate over Flight 587's causes continued for years after the NTSB report was released. Pilots and engineers and safety experts continued to analyze the evidence, to debate the conclusions, to argue about whether the training was really at fault, whether the aircraft design should have been stronger, whether the pilot should have known better. These debates were passionate, sometimes angry, reflecting the high stakes and the deeply held beliefs about safety and responsibility and how complex systems should work. But ultimately, the evidence was clear. The vertical stabilizer separated because it was subjected to loads far beyond its design capability. Those loads were created by rapid, alternating rudder inputs. Those inputs were made by a pilot who had been trained to make them and who believed they were appropriate. The training was flawed. The aircraft could have been designed to withstand more extreme loads. The pilot could have made different choices. All of these things are true, and all of them contributed, and the accident was the result of all of them coming together at the worst possible moment. For New York's Dominican community, the loss was almost incomprehensible in its magnitude and suddenness. The neighborhood of Washington Heights, where Dominican culture and identity had taken deep root, where families had built lives and businesses and community over decades, was devastated. Nearly every family in the community knew someone on that flight. Some families lost multiple members. Children lost parents. Parents lost children. Entire extended families were decimated. The community gathered in churches, in community centers, in homes, in the streets, united in grief that was almost too large to process. There were funerals and memorial services nearly every day for weeks. The community was in shock, trying to understand, trying to cope, trying to support each other through unimaginable loss. The memorial service held in the days after the crash was massive. Thousands of people gathering at venues across the city, politicians and religious leaders speaking, family members sharing memories and photographs, trying to honor those who had been lost. Dominican music played. People embraced. They cried together. They prayed together. Representatives from the Dominican Republic attended. The President of the United States sent representatives. But no words, no ceremonies, no speeches could fill the void left by 265 lives suddenly ended. How do you comfort a community that has lost so many? How do you explain to a child why their parent won't be coming home? How do you make sense of something that makes no sense? In the years since, the Dominican community has worked tirelessly to ensure that those who died are not forgotten. An intersection in Washington Heights, 181st Street and Amsterdam Avenue, in the heart of the neighborhood, was renamed Flight 587 Way. The sign stands as a permanent reminder, a place where people can pause and remember. Every year on November 12th, there is a ceremony. People gather. Names are read aloud. Candles are lit. Memories are shared. Some years, thousands attend. Some years, it's smaller. But it never stops. The community will not forget. In Rockaway Park, the community adjoining Bell Harbor, a memorial was constructed and dedicated on November 12, 2006, the 5th anniversary of the accident, in a ceremony attended by then-Mayor of New York City, Michael Bloomberg. The memorial, designed by Dominican artist Freddy Rodriguez and C2 Studio, is beautiful and moving. It features windows and a doorway, architectural elements that look out toward the nearby Atlantic Ocean, angled specifically toward the Dominican Republic, toward the homeland of so many of the victims. The memorial is inscribed with the names of all 265 victims, 251 passengers, 9 crew members, and 5 people on the ground. Every name is there, carved in stone, permanent, honored. Atop the memorial is a quotation, presented in both Spanish and English, from Dominican poet Pedro Mier. Después no quiero más que paz. Afterwards, I want nothing more than peace. The words capture something essential about the tragedy and the community's response to it. After so much violence, so much loss, so much pain, there was only the desire for peace, for rest, for an end to suffering. The memorial sits beside the Rockaway Beach and Boardwalk, at the south end of Beach 116th Street. It's a place of pilgrimage for many, a place to come and remember, to grieve, to seek that peace that the poet wrote about. In 2007, in a ceremony at Woodlawn Cemetery in the Bronx, 889 unidentified fragments of human remains from the victims were entombed in a group of 4 mausoleum crypts. Even after extensive forensic work, some remains could not be identified with the technology available at the time. Rather than leave them unclaimed and unremembered, community chose to entomb them together, ensuring that even these unidentified fragments would be treated with dignity and respect, would have a final resting place, would be remembered. The Bell Harbor community, too, has worked to memorialize what happened and to support each other. The neighborhood that lost 5 of its own, that saw an aircraft crash into homes where families lived, that experienced trauma on top of trauma after September 11th, has never forgotten. Every year, residents gather at the memorial in Rockaway Park. Names are read aloud, all 265 of them, taking nearly half an hour, every name spoken, every person remembered. A moment of silence is observed at exactly 9:16 a.m., the moment of impact, the moment when 265 lives ended. It's a solemn ritual, a recognition that this tragedy is part of the community's history, part of what binds them together, part of their shared experience. The crash has been extensively documented in various media formats. National Geographic Channel produced an episode of Seconds from Disaster, examining the accident in detail. The episode, titled Plane Crash in Queens, walks through the sequence of events, explains the technical factors, and includes interviews with investigators and witnesses. Other documentaries and news programs have covered the accident. It appears in aviation safety courses and training materials worldwide. Academic papers have been written analyzing various aspects of the accident: the material science, the aerodynamics, the human factors, the training issues. The accident has become a case study in how complex systems can fail, and in the importance of ensuring that all elements, design, training, procedures, oversight, work together correctly. The lessons from Flight 587 continue to save lives today, more than 2 decades after the accident. Every commercial pilot now receives training on the dangers of rapid alternating control inputs. Training programs worldwide have been revised to ensure that simulator scenarios accurately represent real aircraft behavior, and that pilots understand the limitations of structural protection at different speeds. Every simulator session includes discussions about structural limitations, about appropriate control usage, about the differences between what you can do and what you should do. Every aircraft certification now accounts for the possibility of alternating control inputs, ensuring that future aircraft are designed to withstand more extreme conditions than the certification standards of 2001 required. The tragedy has been studied in aviation schools around the world. It appears in training manuals, in safety bulletins, in academic courses on aviation safety and human factors. When instructors teach about wake turbulence, they reference Flight 587 as an example of how proper training matters, how misunderstanding can be deadly, how even well-intentioned responses can be catastrophically wrong. When engineers design aircraft and flight control systems, they think about Flight 587, about how pilots will actually use the controls, about what failure modes need to be considered, about what assumptions might be flawed. When trainers develop simulator scenarios, they think about Flight 587, about the importance of fidelity, about ensuring that simulator behavior matches real aircraft behavior, about making clear what is realistic and what is exaggerated for training purposes. The 265 people who died that morning did not die in vain. Their deaths, terrible as they were, led to changes that have made flying safer for everyone. That's not adequate compensation. Nothing can compensate for the loss of a loved one. But there is some small measure of meaning in knowing that their deaths led to improvements, that other lives have been saved, that other families have been spared similar grief because the lessons were learned and applied. The accident also remains a reminder of how complex aviation safety really is. It's not enough to design strong aircraft, though that's essential. It's not enough to train skilled pilots, though that's essential too. It's not enough to have sophisticated simulators or detailed procedures or robust oversight. All of these elements must work together correctly, and the assumptions underlying each must be valid. When there's a mismatch between what pilots are taught, what they believe, what simulators show, and what aircraft can actually withstand, tragedy can result, even when everyone involved is skilled and professional and trying to do the right thing. The accident highlighted the importance of learning from incidents, not just accidents. The 1997 Flight 903 incident over Miami was a warning sign, a clear indication that there was a problem with pilots using aggressive rudder inputs and with the structural loads those inputs could create. The vertical stabilizer on that flight had experienced loads approaching ultimate load limits. But the incident was investigated, the aircraft was repaired, and the broader lessons weren't fully absorbed. The training wasn't changed. Procedures weren't revised. Warning signs were missed or minimized. It took the loss of 265 lives 4 years later to finally drive home the lesson that should have been learned from an incident where no one died. In aviation safety, we often talk about the Swiss cheese model, developed by psychologist James Reason. Imagine multiple slices of Swiss cheese stacked in a row, each slice representing a defense against accidents: aircraft design, maintenance, training, procedures, oversight, regulations, crew resource management, and so on. Each slice has holes, representing weaknesses or gaps in that particular defense. Normally, the holes don't line up. If one defense fails, the others catch the problem. A design flaw might be caught by maintenance. A training gap might be covered by procedures. A procedural violation might be caught by oversight. But occasionally, rarely, all the holds line up perfectly, creating a path straight through all the defenses. A hazard passes through every layer without being stopped, and an accident results. That's what happened on Flight 587. The aircraft design had characteristics that made it vulnerable to certain types of control inputs. The training program taught those very control inputs as appropriate responses. The simulator reinforced the training without showing the negative consequences. The pilots had misunderstandings about structural protection. The oversight didn't catch the training issues. The certification standards didn't require design for alternating control inputs. All the holes lined up, and 265 people died. The NTSB investigation was one of the most comprehensive in the agency's history. The final report ran to over 300 pages, with extensive technical appendices. Investigators examined the composite materials in unprecedented detail, conducting tests that had never been done before on composite aircraft structures. They interviewed dozens of pilots about training and procedures, documenting the widespread misunderstandings about rudder use and structural protection. They recreated the loads and the vertical stabilizer using sophisticated computer models, validating the models against test data, showing with certainty what forces the structure experienced. They tested material samples and aircraft components. They analyzed maintenance records and design documents. They left absolutely no stone unturned in their search for truth. What they found was an accident that was preventable at multiple points. If the training had been different, emphasizing that rudder should not be used for roll control, Mullen might not have made those inputs. If the simulator had accurately represented the real aircraft's response to control inputs and the structural consequences, pilots might have learned the danger. If the aircraft had been designed with more structural capacity to handle alternating loads, the structure might have survived. If the industry had fully learned the lessons from Flight 903 and similar incidents, procedures might have been changed proactively. Any one of these things might have prevented the accident, but none of them happened. The holes lined up, and the accident occurred with a terrible inevitability, born of accumulated small failures in understanding, communication, and foresight. Today, more than 2 decades after that November morning, commercial aviation is safer than it has ever been. Fatal accidents in major commercial aviation are extraordinarily rare. The accident rate has declined steadily for decades. In 2024, commercial aviation achieved one of its safest years ever, with millions of flights operating safely around the world. And every accident, every incident, every close call contributes to that safety record by teaching lessons that prevent future tragedies. Flight 587 is part of that legacy, a painful lesson bought at terrible cost, but a lesson that has been thoroughly learned and conscientiously applied throughout the global aviation industry. When we board an aircraft today, when we settle into our seats and trust our lives to the pilots and the machine, we are protected by layers of safety measures that have been built up over more than a century of aviation, refined through experience, informed by countless flights and, tragically, by accidents like Flight 587. The training that pilots receive has been refined based on real-world experience, incorporating lessons from accidents and incidents. The aircraft have been designed with deep understanding of how they will actually be operated, how pilots will actually use the controls, what failure modes need to be protected against. The regulations have been written with knowledge of what can go wrong and how to prevent it, constantly updated as new lessons are learned. The families who lost loved ones on Flight 587 can never be fully compensated for their loss. no amount of safety improvements, no number of lives saved, no memorial or ceremony or investigation report can bring back those who died. The pain doesn't end. The grief doesn't stop. Birthdays and anniversaries and holidays are forever marked by absence. But there is some small measure of meaning, some small measure of comfort, perhaps, in knowing that their loved ones' deaths led to changes that have saved other lives, that continue to save lives every day. Every pilot who learns about the dangers of rapid control inputs, every aircraft that's certified to withstand alternating loads, every training program that teaches correct responses to wake turbulence, every simulator that accurately represents real aircraft behavior. These are part of the legacy of those 265 people who boarded a routine flight on a clear November morning and never came home. Captain Edward States and First Officer Sten Moline were professionals doing their jobs to the best of their ability, based on the training and information they had been given. They did not make reckless decisions. They were not negligent. They were not careless. They responded to a wake turbulence encounter using techniques they had been taught, techniques they had practiced in the simulator, techniques they believed were correct based on everything they knew. They were trying to save the aircraft. They were trying to protect their passengers. They were doing what pilots are supposed to do: respond to unexpected situations with trained procedures. The tragedy is that they were wrong, that what they believed was correct was actually catastrophically incorrect, and by the time anyone realized the mistake, it was far too late to correct it. The flight attendants, Deborah Fontakis, Barbara Gianasca, Wilmer Gonzalez, Joseph Lopez, Michelle Mills, Carol Palm, William Valdespino, were working that morning, serving passengers, ensuring safety, doing their jobs with professionalism and care. They had no control over what happened in the cockpit. They had no way to prevent the structural failure. They died without warning, without time to react, killed by forces they couldn't have understood or prevented. They were simply doing their jobs, serving others, trying to ensure a safe and comfortable flight. The passengers were simply traveling. They had lives, families, jobs, plans, dreams. They were going home or going on vacation or going to see family or going on business. They boarded the flight with the reasonable expectation that they would arrive safely at their destination. They trusted in the aircraft, in the crew, in the entire system of aviation safety that makes flying the safest form of long-distance travel. That trust was well placed. The system is remarkably safe. But on that particular morning, in that particular flight, a unique combination of factors came together. The holes in the Swiss cheese aligned, and the system failed them. And the 5 people on the ground, Helen Concannon, Thomas Concannon, Kathleen Lawler, Christopher Lawler, Franco Pomponio, were in their homes, going about their morning routines, living their lives, completely removed from aviation, when an aircraft fell from the sky and ended those lives in an instant. They had no connection to the factors that led to the crash. They made no decisions that contributed. They were simply in the wrong place at the worst possible time. Their deaths are perhaps the cruelest reminder that aviation accidents affect not just those who choose to fly, but sometimes those who are simply living their lives on the ground below the flight paths. The story of Flight 587 is not a simple story of cause and effect, of one factor leading to one outcome. It's a complex web of technology, training, human factors, organizational culture, regulatory oversight, and accident chance. It's a reminder that aviation safety is not a destination to be reached, but a journey to be continued, not a finished product, but an ongoing process of learning and improvement. Every flight that lands safely is a victory. Not because failure is likely, failure is exceedingly rare, but because safety requires constant vigilance, continuous learning, honest self-assessment, and the willingness to change based on new information, even when that change is difficult or expensive. The morning of November 12, 2001, dawned clear and beautiful over New York City. The sun rose over the Atlantic Ocean, painting the sky in brilliant colors. The air was crisp and cool. It was a kind of morning that makes you glad to be alive, that makes you appreciate the beauty of the world. 265 people woke up that morning, got dressed, ate breakfast, kissed loved ones goodbye, and headed to the airport or stayed home to begin their day. By mid-morning, all of them were gone. Their families' lives were forever changed. Two communities, Dominican New York and Bell Harbor, were traumatized in ways that persist to this day. And the aviation industry was forced to confront uncomfortable truths about training, design, and the limits of our understanding. But from that tragedy came change, real, meaningful, lasting change. The industry learned. Procedures were revised. Training was fundamentally improved. Aircraft were redesigned with better structural margins. Simulators were improved and validated. Oversight was enhanced. And today, the skies are safer. Not perfectly safe. Nothing involving complex technology operated by humans in challenging conditions can ever be perfectly safe. But safer than they were. Demonstrably, measurably safer. That's the legacy of Flight 587. That's what those 265 people, who never asked to be part of aviation history, who simply wanted to travel from New York to Santo Domingo on a November morning, gave to the world. The vertical stabilizer recovered from Jamaica Bay after extensive testing and analysis, after serving its role in the investigation, sits in storage as a piece of evidence, a reminder of what happened and why. The memorial in Rockaway Park stands facing the Atlantic, its windows open to the horizon, names inscribed in stone for all time. In Washington Heights, residents passed the sign reading Flight 587 Way, and remember. In Dominican Republic, in towns and cities across that island nation, memorials honor those who died. And in aviation training centers around the world, in classrooms and simulators and briefing rooms, instructors teach new generations of pilots about wake turbulence, about control inputs, about structural limits, about the importance of understanding not just how to fly, but why certain techniques work and others don't. And they reference Flight 587 as an example of what can go wrong when the pieces don't fit together correctly. The flight recorders have been silenced, their data extracted and analyzed and incorporated into the final report. The investigation is complete, the reports filed, the recommendations issued and largely implemented. The aircraft is gone, broken into thousands of pieces, dispersed across Bell Harbor, some pieces kept as evidence, others disposed of after the investigation concluded. But the memory endures. The families remember. How could they forget? The communities remember, gathering each year on November 12th to read names and observe silence and light candles. And the aviation industry remembers, carrying forward the knowledge bought at such terrible cost, ensuring that the lessons continue to inform training and design and operations. Good night, and safe travels. May the lessons of Flight 587 continue to protect those who fly, today and always, in every corner of the world where aircraft take to the sky. May those who died be remembered, not just for how they died, but for the lives they lived, the people they loved, the dreams they held, the communities they were part of. May their families find peace, even as they continue to miss those who were taken from them. And may we never forget that safety is not an accident, not a gift, not something that happens automatically. but the result of constant vigilance, honest investigation, difficult conversations, expensive changes, and the courage to admit when we're wrong and to change course even when it's hard. The sky is safer tonight because of what was learned from that clear November morning. That is their legacy. That is how they are honored. That is why we tell their story. Good night.